You know that feeling when you're staring at a math problem and it just feels impossible, like a locked box with no key. But then someone hands you this secret key, and not only does it solve the puzzle, it reveals this incredible hidden world you never even knew was there. Well, today, we're going to dive into one of those puzzles.
So, the big question for today is this. How on earth do you divide by the square root of -1? I mean, how do you divide by I? Or really, any number that has an I on it? It's kind of like trying to divide by a ghost, right? You can add them, subtract them, you could even multiply them, but division? Oh, that is a whole different ballgame.
All right, so just to make sure we're all starting from the same place, let's do a super quick refresh. A complex number, right, it's got two parts. You've got the real part, A, and then you have the imaginary part, B, which is attached to our good friend, I. And the one rule you have to remember, the golden rule of this whole world, is that I squared equals -1. Simple as that. Okay, so when you start working with these numbers, things can feel a little familiar at first. It's like you're stepping into this world with a strange new kind of math. And hey, some of the old rules seem to work just fine, but not all of them. I mean, look at this. Addition and subtraction. Super easy. You just combine the like terms, you put the real parts with the real parts, imaginary with imaginary, done. Multiplication is a little more work, sure. You just FOIL it out, like you do in algebra, and simplify things down. But division, yeah, that's where we hit a wall. All those question marks. What do you do when you have an I sitting in the bottom of a fraction? So, to get around this problem, mathematicians came up with this really clever, well, it almost feels like a magic trick. In school, it's usually just taught as the procedure or the trick to get the right answer. But trust me, as we're about to see, it's so much more than just a trick. All right, here are the steps. It's pretty mechanical. First, you write out the division problem as a fraction. Easy. Second, you find this thing called the complex conjugate of the denominator, the bottom number. Then, and this is the really important part, you multiply both the top and the bottom of that fraction by the conjugate. And finally, you just do the algebra, clean it all up, and simplify. Okay, enough with the theory. Let's make this real. Let's get our hands dirty with an actual example. We're going to try to divide 10 plus 5i by 4 minus 3i. So, what exactly is this magic ingredient, this complex conjugate? Honestly, it's shockingly simple. All you do is take a complex number and you flip the sign on the imaginary part. That's literally it. So the conjugate of a plus bi becomes a minus bi. So for our problem, right, the denominator is 4 times 3i. To get the conjugate, we just flip that minus sign on the imaginary part to a plus, and boom, we get 4 plus 3i. See? Easy. All right, on to step 3. We take our conjugates, and we multiply our original fraction by the conjugate divided by itself. Now remember, anything divided by itself is just 1, right? So we're not actually changing the value of our number, we're just changing how it looks. And in doing so, we've turned this tricky division problem into just a big, messy multiplication problem. Okay, now I'm not going to bore you with all the nitty-gritty algebra on screen, but trust me, after you multiply out the top, multiply out the bottom, and simplify everything, you are left with this beautifully simple answer, 1 plus 2i. So the process clearly works, the trick did its job. But it still kind of feels like magic, doesn't it? Which leaves us with one giant question. Yeah, it's time to look behind the curtain. We're going to stop treating this like a magic trick and start understanding how the lock actually works. It's time to unlock the real secret of the conjugate. And this is the question, right? This is what separates just following the rules from really getting it. Why? Why does this weird, seemingly random trick of multiplying by the conjugate actually work? How does it make that pesky imaginary number in the denominator just disappear? Okay, here it is, the big secret. The superpower of the conjugate is what happens when you multiply it by the number it came from. When you do that, the result is always a real number, no exceptions. The imaginary parts just, poof, vanish completely. And you can see it right here in the algebra. When you multiply a plus bi times a minus bi, look what happens. Those two middle terms, the plus abi and the minus abi, they cancel each other out perfectly, every time. Then you're left with that I squared, which we know is just -1. That flips the last sign, and you end up with a squared plus b squared. And that is always, always a real number. So you see, the big takeaway here is that the conjugate method isn't really a trick at all. It's a precision tool. It has one job and one job only, to force the denominator to become a real number. Because once the denominator is a plain old real number, well then, division is easy.
But the story doesn't end there. Not even close. We've answered the how this works, but there's a much deeper, much cooler why. And to see it, we have to completely change how we're looking at these numbers. We have to stop thinking about algebra and start thinking about geometry.
This right here, this is the big moment, the pivot. It turns out that everything we've been doing with these symbols on a page, it's not just abstract math. It's a description of movement, of rotation, of scaling in the real world. This isn't just algebra, folks. It's geometry.
So, picture this. Instead of thinking of a complex number, a plus b, as just a formula, think of it as a coordinate, a point, a, b, on a graph. Now draw an arrow from the center, from the origin, out to that point. That arrow is a vector. And every single vector like this has two key properties. How long it is, we call that its magnitude, and which way it's pointing, that's its angle. And here it is. This is the secret key to the whole kingdom. This is the geometric rule for multiplication. When you multiply two of these complex numbers together, you are doing two very simple things. You multiply their lengths together, and you add their angles together. That's it. It's this beautiful, simple rule that turns all that messy algebra into something you can actually see, something clean and intuitive.
And this one single idea that multiplying these numbers is really just about rotating and scaling, that's what unlocks everything. It's the reason complex numbers are so incredibly important for understanding the physical world around us.
So that's the big idea, right there. Every single time you multiply by a complex number, what you're really doing is performing a transformation. You're rotating something by that number's angle, and you're scaling it, stretching or shrinking it by that number's length. And that is a cornerstone of physics, engineering, computer graphics, you name it. And it gets even cooler, believe it or not. This whole system elegantly combines two super important ideas from physics. Get this. When you multiply the conjugate of one number, let's call it A, by another number B, the result is amazing. The real part of the answer is the dot product. That tells you how aligned the two vectors are. And the imaginary part of the answer, that's the cross product, which gives you a whole new vector pointing perpendicular to the first two. I mean, two fundamental concepts, all wrapped up in one single beautiful operation. It's no wonder this stuff is absolutely essential for things like signal processing, physics, and engineering. Which kind of brings us full circle to this final thought. We call them imaginary numbers, right? But they give us the perfect language to describe incredibly real things, like rotations, waves, electrical signals, stuff that makes up our actual physical world. So it makes you wonder, if these numbers are the key to describing reality, how imaginary are they, really?